well as opportunities. So these are opportunities based on the resources that are available, and they're in the energy efficiency and renewable energy space. With this, you try to identify the best next steps that a nation can do to achieve these priorities and funnel the limited resources for getting additional funding and project implementation into these best next steps. I also wanted to add this comment about load modeling. I have an energy efficiency background as well, and I love being in spaces where you think this building probably has an automation system based on a CO2 occupancy sensor that's going to identify how many people are in the room and change the airflow. That's not what you get with microgrid modeling. Really often you're working with a remote community that maybe has a couple of years of measured data out of the past 10. If you're super lucky, they maybe have a current data logger. And if you're incredibly lucky, that data won't get erased when you go to upload it and then use it for some of your assumptions. So this is with the Much First Nation. We have the Equal Wave project underway with them in partnership with UVic. You would think I would talk about this project today, but I'm not going to talk about it very much. What I just really want to highlight is that this project is based on in Uquat, which currently has one house, and they are saying that they're going to return home, and over 15 years they're going to have seasonal and permanent homes in place, as well as ecotourism. So we're now trying to build a microgrid for a load that does not exist, and we are trying to bring together all of the planning that the community has done to identify what that load might look like. The level of data that you have for the next steps of this process are always going to be limited by the fact that these load assumptions are wrong. There is no way that this is right. Hopefully it's pretty close, and maybe it's not. And so just really like keeping in mind that you will be wrong in this process. Your microgrid model results will be wrong, and hopefully they'll only be a little bit wrong. And just being really comfortable with that and being able to narrow down how they're wrong and the implications that has. I think you'll be hearing from a few different people that work with Anthony today. One of the reasons that people really like to work with Anthony is because he understands the details of the models that he's using. He can tell you what equations were used. He can estimate the outputs of them before he runs them. And that means that you understand sort of the level of error, what impact different factors are having. And that is absolutely critical in knowing whether you should trust your model or not. So the project that I'm going to talk about is, as I said, the Tap Creek Hydropower Project with Heshquit First Nation. This is in Hot Springs Cove on the west coast of Vancouver Island. It's a remote independent microgrid with a population around 150. We're talking a lot about being wrong. I reserve the right to be wrong about any of the details that I'm about to share. I worked on this project for a couple of years. I've been at Barkley for 10 years now. I did not work on this project from start to finish, and I'm just sort of presenting it because it's an interesting example of the information that you start with and the product that you get at the end. This isn't the funnest slide that I've ever made, but basically what it shows you is when we look at sort of our categories of data that we use in microgrid modeling, our resource data, our load data, and our project design and costing, we are going through these different development stages and revising each of these data sources at each one. Throughout this process, I'm going to try to give you some financial numbers about how much it cost to move through each phase of this project. I reserve the right to be wrong, I will remind you. So when we start with the pre-feasibility stage, this is all at a computer. We're doing desktop GIS, we're looking at historic data and reports, and we're looking at industry standards for project costing and estimated design. As we move into feasibility, we get more specific LiDAR for the site. We're starting to get measured load data from the community, as well as getting our initial on-the-ground idea of what the project might look like, and that initial design that helps us streamline things like our penstock. This is a hydropower project, so our penstock length, our transmission line length, where the road might go, what the permitting process might look like. And then we moved into detailed design. By the time you're getting the data that you might consider to not be garbage, we've spent $800,000 on this project. That's when you have your hydrometric program in place, you have resource data that is specific to that stream, you have a couple years of measured load data for the community, and you have the details of all the infrastructure pieces that are going to feed into the cost of the project and the complexity overall. During the construction stage, you get to find out how right or wrong you were as you get your actual costs, your as-builts change the design, and then during operations, as you look at your actual performance, you have that continued load modeling and the actual operation costs. One thing that will be highlighted as we go through this as well is that I'm talking about being right or wrong, but it's also always changing. So right in one minute will probably be wrong in the next one. When we talk about load data, our load from this year is not going to be the same as our load for next year. Is there going to be climate change, a drought, an increase in population, infrastructure development, a global pandemic? These are things that you just don't know that are going to impact the results. So diving into some of the details here about the Tap Creek Hydropower project. In 1985, an engineering study first identified the Hot Springs Cove Creek, which is now called a TAP, as the best hydropower and clean energy option for the community. You see a nameplate of 400 kilowatts, a gross head of 130 meters, a penstock of 1,500 meters, and 0.097 meters cubed of average flow. We see that another creek was identified decades later at 500 kilowatts, Heshkut Point Creek, and then a BC Hydro Remote Community Electrification Program in 2013 identified Hot Springs Cove Creek again, a tap creek, with a nameplate of 200 kilowatts and a gross head of 200 meters. This is where Barkley sort of enters the picture. My understanding is that at this time, the BC Hydro Remote Community Electrification Program, Greg can correct me, went on an indefinite pause, and Heshkut First Nation decided to go ahead with their own upgrades based on some of the recommendations that this plan had and the cost that would be required to update their diesel to be of current standard, BC Hydro standard, which they did not meet at the time. So the first thing that they did upon receiving that report and deciding to sort of do this on their own is the pre-feasibility study. They received $50,000 from Clean Energy Business Fund, and during that it was identified as a 250 kilowatt project, 200 meters. You're starting to get some penstock length and hydropower penetration expectations shared with the community. So 98% is really close to being 100% renewable, which is the objective of Heshkut First Nation. We also have some load data that came from hourly measurements from 2010 and 2011, showing a load of 725 megawatt hours per year, as well as some detailed averages and maxes in there. And you can see here, you're going to be looking at a summer low flow period that's really going to be the reason that you're not going to have 100% penetration. And you're starting to set even more expectations by putting the community on a map, showing them a creek that they know, and starting to lay out actual project components and how they might look. So nearly $200,000 was received for feasibility phase 1 and 2 after this. This is when you really start to get a lot of engineering, environmental, and permitting teams on site. You're doing your site reconnaissance, you're implementing your hydrometric program, which is where you're actually measuring the hydrology of the stream so that you can calculate the resource available, your generation modeling, you're continuing your community meter install, and you're improving all of your infrastructure estimates with actual LiDAR on site and other de-risking activities. So terrain stability assessment, for example, was identified here. You can see that our load has increased fairly substantially since we used the 2010-2011. We're now at 844 megawatt hours. Tough news, our hydropower penetration has dropped to 78%, so a 20% reduction in our first iteration. Phase 3, we continue to work through the tertiary sort of components that support the project. This one had a road design that went through a park, which was a high permitting risk, seismic refraction surveys, hydropower designs, getting ready for understanding the cost of constructability on site. So while the engineering teams are doing this, we're also getting outputs of the resource penetration and when you're going to see diesel supply. And so you're seeing again this high summer diesel use, as well as some sort of intermittent throughout the year gaps. In 2017, maybe just to back up for a second. So these were funded by FNIP, First Nation Infrastructure Investment Program, which is through INAC at the time, ISK now, ISD. So they have their own requirements that they would like to see during this time as well. They're wanting to see the project de-risk in a certain path. You're also going to have other funders that are wanting to see their own outcomes, but FNIP in particular will tell you what they're going to fund. So at the time, they would not fund anything other than hydro. We're starting with hydropower. This was the best bang for your buck. Let's see this project through. We're also not going to be forecasting growth. We're going to build for what exists here because our data is showing that unreserved communities and remote locations are not growing. So we're hearing from the community, we'd like to have space to grow here. We're hearing from the funder and the program manager that's not going to happen in this iteration. The tone starts to change a little bit in 2017. And that's when we're able to start to first look at how we can address that more clearly visualized gap in the summer where there's not going to be enough hydropower. This is a time where there was more money around for remote community energy development and diesel displacement. And so we completed our first homer analysis for the project at this time and did an analysis based on the reservoir size that the hydropower facility had to try to right size a solar system and see when your where your greatest return was. And so you can see that between 150 and 200 kilowatt solar capacity was identified as being ideal. And we estimated based on our roof sizing and ground availability that 178 kilowatts of diesel would work and would be our lowest cost of energy. In 2018, we get the final design. As I said, the programs are changing and the appetite for additional renewable is changing. So we've now changed the project all of a sudden. It's now a 350 kilowatt project. We've only gotten 2% more hydropower penetration with that, but part of what we've gotten is this really good case now for future fuel switching in the community, for people moving away from fossil fuel heating to electric, and as well as to for future development in the community as the community had wanted previously. Our load is continuing to grow. We're now at 876 megawatt hours, and now we have 3 years of actual load data for the site. In 2021, solar construction started first before the hydropower project, which I think was hard for people that had just worked for 8 years on the hydropower project, but that's the beauty of solar. It's pretty implementable in comparison to these more complex hydropower projects. And so it was started first, and then the electrical tie-in component was happening at the same time that the hydropower project was being constructed. Based on actual roof availability and contractor design, the PV was reduced without any microgrid modeling from 178 kilowatts to 115 kilowatts. At the same time, we were telling the funders in the program, a battery system would be really helpful here in optimizing the operations. Battery technology had changed drastically from 2013 to 2021, and I really want to highlight that. And there was an appetite to hear it, but as you'll recall, we have other fish to fry. We are at the pre-construction stage of the Atap Creek Hydropower Project. Coming in, $4 million more than anticipated back in 2016 at $14 million. The hydropower construction was also completed in 2021. It's kind of interesting because this hydropower performance graph looks a lot like some of the estimates that we saw beforehand, which means that we were wrong, but maybe not too wrong. And it really starts to highlight some of the areas where we might be able to improve diesel displacement further in community. So what you're seeing on this graph is an area, this is not unusual in the first year of operations, where the facility was shut down during a low flow period for maintenance and repairs, as well as, I think I show this maybe better on this one here. You can see that because we have PV, but we don't have a battery, every day you're using the solar for half the day, and then even though you could produce more, you're not capturing it, and then it's lost in the evening. So you're having this diurnal use of diesel on a daily basis, which is starting to create that governing battery system case a little bit further. what else should we point out here? Look at that energy use, 956,869 kilowatt hours. So the load in the community is continuing to increase rather dramatically, and this is expected. When people know that you no longer are working off of diesel, the narrative is that you have this hydropower project that is going to make most of your community renewable energy. People are plugging in those space heaters. They're going to do some behavioral changes that will spike your energy use in community.
Was the hydro plants the same and like physical assets the same variability of output?
Yes, that's correct. Yeah. There was a diesel improvement here. I'm not sure what year that was, but the diesel systems were upgraded during this time as well. So you will see some slight decrease in diesel because of increased efficiency to now match the sizing of the hydropower. So luckily in 2025 through the CEDAR program, the nation was able to look at the performance data to date and say it's now time to look at our battery governing system and get something installed. So in May of this year, they installed a 440 kilowatt hour BESS to add to this 350 kilowatts of hydropower and 150 kilowatt hour of solar. And it's estimated to have a 25% diesel reduction in the first 3 months. The main reason that it's saving diesel, well, there's a few different ways, but one of them is that you're not having to run your diesel in the background in case your load all of a sudden peaks above what the solar and hydropower are able to provide. And because of that, you're able to have sort of this idling in the background really quiet down, as well as cycle charging your generators. So you're running them at peak efficiency and then turning them off and the battery's taking over, and then you're going back and forth. Okay, some additional things to consider, just to make sure this gets less cohesive now again, is that in 2024, we were able to figure out for the first time what some specific buildings were using for their energy consumption. All of this was done without per building metering. So a long way away from CO2 sensors in a building like this, we had the lump sum for the community. Lump sum at the powerhouse or the generator station, so that includes all the transmission losses and things like this. But having per building metering is super important for communicating to people how they're using energy. If you want to implement a utility-like metering structure, before this is a base case, you paid $20 a month for utilities. Do you have a grow up in your basement? Do you live in a passive house? It doesn't matter. Your utility is the same cost across the board. This starts to set the stage for conversations like, hey, you're using 5 times as much energy as your neighbor. Are there housing improvements that could be done to help you reduce those costs? Is it because of things that is it a need for additional housing? What is causing these? And it helps you start to pinpoint that other sort of demand side use a little bit more. I'm not being defensive, but I just want to remind you that Homer wasn't released until 2014. And in some ways, I really stick behind, in many ways, the Excel-based modeling that some of this was done on. All of the assumptions were understood and could be communicated really clearly. And when things were changing, you are able to really identify the change and the impact of those. Obviously, with the complexity of how microgrids operate, you're also losing some functionality around that. One of the biggest concerns about Homer and other microgrid modeling software is that it does have the hindsight of 2020 vision. You can see, how would I operate this knowing that the next day is going to have lower solar potential and the load is going to go like this? Operators don't know that in community. And you also don't have a team of UVic engineers every day to help model this. You have remote people operating these projects that need to have reliable power. More important than optimization is safety and power and making sure that people get those things. No offense. This is where I really reserve the right to be wrong, but a reminder that we've seen tremendous decreases in the cost of battery and solar. And at the same time, we've seen the cost of implementing small-scale hydropower more than double in BC because of the cost of construction. And so you're seeing this, the microgrid modeling that we did about sort of best case options for projects that haven't been developed yet are now really different than what they'll actually be because of that high and still increasing cost of hydropower implementation. I'm hoping that what you got from this sort of long-winded spiel is that there's a lot of changes in the design specifications, and these are because of changes to coming from the environmental team, the permitting team. Your seismic team is telling you can't build there. It's now a different penstock route. It's a different road route, whatever it is, and this changes the costs and the performance, and so things are always changing. And that microgrid modeling is trying to capture in time a bit of a moving target. Oh, I had even more to ponder. Let's see what it was. Okay, so I think this is all sort of just repeating it, but it's really about identifying what data you can get at what time, what the time and cost requirements are to get that data, what it's actually improving, and how you communicate that to the community. Specifically, you may be choosing to do things in the background that you're not communicating because you know this iteration is going to change 5 times in the next year. Let's not put that on a community presentation yet because we don't want them to learn 5 different numbers. Once that settles, we can give them a more sort of final result or anchored result. Yeah, I'm gonna leave it there. That's too many words. Thanks. Any questions? Yes, Steve.
You talked about behavior change. Maybe this is a question for the anthropologists in the room too. I've certainly noticed in my work, as soon as you give somebody a reliable energy system, they start consuming more energy, not less energy. In some cases, a lot more. I was wondering how you incorporated that into your modeling.
Yeah, that's a good question. I think this was first called the Prius effect, right? When people started to get a Prius and now they'd all of a sudden drive to the mailbox because it no longer used as much gasoline, but now they're driving everywhere. I think it's one of those things that you incorporate into your forecasting assumptions overall. And you really sort of put that list of what's going to change your load forecasting into a pile and you see sort of what the net changes are within that. In some communities, you'll get a really clear mandate. Riley and I are working with Kwikwasidna We know that eliminating propane is a really high priority, both at a leadership and community level. We expect as other energy sources get in there to see this really rapid fuel switching. In other communities, people are like, I kind of like it. It's super reliable. I know it's there. I'm going to be more resistant. So it's going to be per community basis. That's part of the beauty of the community energy planning process is like from the beginning, you understand the priorities and the narratives that are circulating within the community, and those will impact uptake and behavior change.
In one instance, we had a project where we engaged with everybody in the commercial project. So all your tenants, residential and commercial, were part of the narrative. So they got to see the energy production that their building was generating, and they could see their water consumption reductions and their energy reductions on a per unit basis, anonymously, of course. But they could see that they could be part of the story going on in the building itself. So, and there was some incentivization that went along with it. You know, it's super users or super non-users. You know, business in Seattle is getting a Starbucks gift card once a month to win it, right? And it was all part of that. Felt like they were part of that solution.
Yeah, I mean, that's a great point. As I mentioned maybe a couple of times here, community members in this community are living in a complete void of understanding of how much energy they're consuming because they're never being presented any of that information. They know whether they're comfortable in their house or not, and that's sort of the extent of that. And obviously, depending on homes, home quality, that doesn't necessarily even reflect energy use. So really bringing that knowledge and whatever information you can is super useful. One way we start to sort of increase energy literacy passively in these communities is by having, when we put those smart meters in, having them actually displayed in the lobby. So people are able to, or in the entryway on tablets or whatever it may be, people can go and look at how much energy consumption the building's actually using and start to get familiar with that entire sort of concept and what it could mean in terms of how they use it. Yeah.
You mentioned obviously like cost of some energies went down, some energies went up.
Mhm.
Your colleague also mentioned about like innovation in the space. Like, how do you model that into the whole kind of like economic projection of projects?
Yeah, it's hard. I think that the important thing is knowing your assumptions. Your assumptions are going to change, and you just use the information that you have at the time, and you keep tabs and you flag the information that you think is going to change over time. Information that you want more detail of to de-risk, and that is going to have just like project design changes. But Andrew and I have a lot of conversations around like, what are we going to do for assuming cost of battery when you need to replace this system during the lifetime? Like, what do we think the cost of battery is going to be in 15 years? I don't know. Like that, it's really some of those key areas of guessing. I don't know if you're allowed to say guessing in this space, but I think that like you really need to identify where those are and sort of own them and set like embed that in your expectations. This is not like a magic 8 ball. These are our best guesses.
And follow up to that, how does the community kind of like take those assumptions? Like, are they okay with you kind of being open with presenting guesses, or are they wanting more like hard numbers?
Yeah, I think that one of the things that Barkley Project Group does pretty well is the relationship building side of things. We have our key contacts within the community that are sort of more along for the ride. Somebody in the administration, sometimes the council of chiefs or chief and council, and sometimes community energy champions. But there are some people in community who have a really good idea of all these little changes that are happening, and then the general community maybe isn't seeing all of those. But then they also have somebody internally who also understands the changing context in the community that can speak to some of those. There's a wariness in Indigenous communities about consultants, and I think that there should be. I think whenever resources from a community are being spent externally, there should be high expectations about that. And so really making sure that when I talk about like not sharing all of the iterations, you're sharing them with somebody, you're communicating why you're doing them and justifying them, and the level of buy-in from that community member can be, or administration person can be really helpful. We work with Azar Cameron, who's the CEO and tribal administrator at Mowachut Munchlett for the WAVE project. Now that's a project that's had some changes. And the other benefit of that project, just to go back to that one for a sec, is that they have a hereditary electoral system. So their council of chiefs is the same council of chiefs as when we started the project. There's no voting, there's no changeover. It's just a hereditary pass down, which means that we've had that continual buy-in, and we have leaders in the community that can speak to how we made decisions at each point and how we got there. And that's been really useful in smoothing over what I think would be some challenging pivots that have happened without that. If this is about discount rate, I don't want to hear it, Andrew. Well, what do you got?
To sort of share my learned perspective from private industry on like that integration of technologies piece. And when I get the go ahead to do something like that, I'm thrilled. I love it. And I dive right into it, and you can detail cost benefit analyses, come up with all kinds of fun conclusions. But it's really rare when that happens because we're constrained by the budgets that we have to execute on projects, and we have specific objectives to accomplish within those budgets. And cost benefit analyses, the hard truth is that they cost a fortune, and they're tons of fun and they're great, but we can't often justify it. And I think that's where academia could really step in and help us out in what we're doing by feeding in those kinds of results from looking at like digital system integration and grid management and all that fun stuff. Like that's something I wanted to dig into for a long time, but it's going to cost like $15,000 to do it, so I can't do it. You know.
Yeah, good point. Thanks, Andrew.
First of all, your presentation was awesome. I particularly liked presenting the cohort results and then presenting the real measured results, because I feel like in my research we don't often get that.
Right.
I'm being super long-term forecasting. I had two questions. One was, did you consider several scenarios in terms of accounting for uncertainty in, say, like load or technology costs in the preliminary modeling work? And then secondly, more generally, how did you encode those other community values that are like not just cost optionality into your modeling process?
Yeah, great. I think one of the main things that we incorporated in terms of alternate scenarios in here was the impacts of climate change. Having alternate models where you're identifying, we have a 20-year synthetic flow that gets higher in sort of accuracy over time because we connect it to the actual hydrology in the stream. You're able to pull out low flow years compared to average flow years and run those. So towards the end of this, in the last year or 2 years, we're starting to have low, average, and medium, low, average, and high renewable penetration scenarios, and explaining that they can be based on a variety of things that are impacting the resource size more than anything. Our load, as I mentioned, our load forecasting for this one was pretty minimal. We were really working about like what happened last year was our design load. And in some ways that was easier. You know, you're able to just communicate that. The quant wave one that we started with looking at there in these different sort of year 0, year 5, year 10, year 15, that is a lot trickier. And it's really an iterative one where we have a spreadsheet that has, this is what we estimate a energy efficiency house, a non-energy efficient house, the seasonal loads, these different scenarios, and you can rebuild these sort of custom scenarios and you can add in loads or remove loads just like with different values. And so you're able to have informal conversation to see like the resilience of the system in different scenarios without necessarily putting all of those iterations into reports and packaging them all up. It helps you sort of see where your high diesel use is likely to be under different sort of scenarios. I think you asked a whole other question that I didn't answer.
Sorry.
Okay.
The second question was on the community engagement side and determining those other values beyond just cost optimization, and how did you encode and consider those in your modeling process?
Yeah, so I think, you know, a lot of what happens in project development is mitigation by design. And so one of the things that you're mitigating is negative community impacts based on what you've heard. And so things like where your road placement goes, if there's specific areas with CMTs or sacred areas along a creek, you're not going to build project components in those. So they're not necessarily going to be within the microgrid model themselves. They're going to be embedded in the design, and then the generation profile from that is going to then reflect those inherently. I think one really important thing that you learn is the narratives, as I said, that are sticky in the community, and you understand that there are some things that you shouldn't say, some things that are not motivators for the community, and other things that really are. Going back to the UQuad example, UQuad was the place of like first contact for colonizers on the West Coast. It is an area that much have lived since time immemorial. There is just like a tremendous archaeological value there. And if you talk about anything related to the project and you're not going to talk about the impact to ground conditions and archaeology, then don't say anything, because their first question is going to be like, well, what's the impact on that? And if you can't like be ready with that, then there's going to be like a lack of buy-in already. So just like really, I think it's in the design, and then it's also in the narrative that you surround the actual results with.
Thank you so much.
Mm-hmm. Yeah, Steve.
You talked about the diurnal nature of solar,
Mm-hmm.
and that batteries can mitigate that by storing sunlight produced at nighttime.
Mm-hmm.
But even so, there still is instances once your batteries are full that there still can be some solar curtailment that happens.
Mm-hmm.
Have you found that the modeling software that you guys, the models that you use are actually relatively accurate at predicting the amount of curtailment in the system?
Yeah, that's a good question. I don't know. For this one, I don't know. We're also working with a reservoir that you can, it's a 6-meter reservoir for the hydropower facility. So you could be optimizing the use of that. Yeah, if you have all the knowledge that exists out there in the sensors. The reality is that it's not operating on that sort of optimized level. It's not forecasting the rainfall for the next week and doing the sorts of things that would be required for that. So
You guys ever use solar to pump water back up into the reservoir?
no, not yet. Sounds good.
I have a question and a deep dive discussion. So first of all, thank you for the presentation. I agree with all your takeaways points. They're refreshing to see. The question is around the charge cycling control of the system. So my understanding is that you're using the battery and charge cycling control.
Yeah.
And so you have the hydro system, diesel system, the solar, and the battery. So you use the battery, and correct me if I'm wrong, you use the hydro as a constant resource or some form of load volume. My guess is constant resource. You use the solar as a negative load, and you have the battery system in grid forming mode at all times, and then use the diesel generator to turn on at peak efficiency to charge up the diesel or to charge up the battery when necessary. Is that correct?
Yeah, or when you're getting too close to that peaking threshold, that will change depending on time of year. But that's right. Hydropower is the primary source here, so you are still seeing that solar curtailment because you're using hydropower first.
Do you have any practical and pragmatic lessons learned from this type of control? This is also used in Colville Lake, and for example, we see more utilization of their switchgear, which means that they're replaced more frequently as compared to a typical other control. Do you find that the charging and discharging the battery, use it more often than say a load cycling control, or even say, for example, if you have a high amount of solar on the system with hydro, do you find that there are more transient events or frequency deviations due to the inertia of the hydro versus the diesel generator? Do you have any specific insights from this specific control philosophy?
Yeah, so we work specifically with a gentleman named John Wheeler, who you may be aware of. He really works in remote Indigenous communities and understands the reality of operating in non-optimized scenarios. I think that one of the what was I going to say? I don't know what I was going to say. I'll come back to you on that if that's okay. Yeah. Yeah, I think that, with it only operating for 3 months, we'll see sort of how it changes. And we have these estimates of what would have happened without it. And we had the estimates of what would have happened with solar. But whenever you're comparing to this other scenario that didn't exist, it's another sort of unknown. And I think that this idea of what infrastructure you're using faster and like whether cycling through your batteries faster and getting through that lifespan mattered a lot more 10 years ago than maybe it does now as the replacement cost of batteries decreases. And so we can sort of get back into that loop of your replacement costs and all of that really having a big impact on what matters or not in terms of like your operating philosophy. Yeah, please.
You're totally right about the technology, right? We've seen a huge drop in battery prices. At the same time, we've also seen the cycle life of batteries increase quite a bit. So you're now seeing batteries with 10,000 cycles, right? Whereas 5 years ago, they had 3,000 cycles. The other thing that's happening is typically in the past, you would have looked at the generators being right? You would follow along with the generator. The generator was the grid forming. As battery prices, solar prices, everything drop, the industry is almost switching now and saying, well, let's take the solar and the battery as the grid forming part, and we're going to get the generator to follow along behind us. That provides a lot more stability with the grid or with the microgrid, because inverters are typically a lot more stable with the battery system than, say, a generator is. So you're only bringing the generator on, as you point out, when the battery gets down to 15, 20%, whatever battery level was. So it's changing dramatically.
Just comment for that. Would it necessitate replacing the entire battery system, or is it a modular plug and play? Because as modular batteries are, if you take a new technology battery, you can't necessarily replace the new battery management system and replace one module out for the other. What would be the strategy on ongoing replacement of the batteries with the newer technologies and integrating it into a battery system that still mostly works? Yeah. And the second thing is, I agree with you with regards to inverter-based resources, but another technical issue is the fault current provided by inverter-based resources. They 10 per unit as opposed to 6 per unit for rotating machinery, and the system was designed for electrical rotating machinery. Is that being considered when suggesting using strictly invert-based resources to power isolated systems?
Well, I mean, again, to answer your second question first, you have to size the system properly to make sure that your batteries and inverters and everything can handle, you know, the loads that you're going to be putting on, right? And while it's true that, you know, spinning inertia can sometimes be a little bit higher than battery inertia, that just is a matter of making sure your battery system is sized properly so that you can get the currents out of it for it. Going back to your first question, if I can.
Oh, sorry. So for example, like the new battery technology may be better, but how plug and play is it? Let's say you want to replace one module with another, or even supply chain or battery manufacturers might not see a remote system and say that's economically not worth it. You have to have 10 megawatt hours or more in order for us to consider supplying modules.
Yeah, so I think what the manufacturers say, and that's real. They say it's fairly plug and play as batteries. I would say that's probably true in the first couple of years. But once you get a few years down, you know, putting a new battery in with a bunch of old batteries can be complicated. Less so with lithium than it was, say, but I know typically we model battery replacement every 10, 15 years.
It's about what we use, yeah.
Yeah. And again, Mary's right. We don't know what battery technology we're going to test in 10 years.
Maybe just add to that, like part of what we do is the procurement process of different contractors. It's useful to know if your contractor will exist in 10 to 15 years, and try to select one that is more likely to. And you'll really often have lowball offers from folks that are just like breaking into the field and are interested. It's probably not worth it for your project to be the guinea pig for a company that might not exist or might merge in a way that that sort of knowledge of the system is lost in that shuffle, and really being mindful of the experts that you're bringing onto the team and their longevity, I think is a key sort of project management tip during procurement. Thanks, everybody. Oh,
But just on there, the metering thing, so what in that's good. What is the actual local metering, and is every resident paying individually for energy, or
so in this community right now, the community buildings are now metered individually, and the overall community is metered, but the homes are not metered yet. That's like part of the next stage of this process. To look at Wikino, for example, with the Niknikwit hydropower project, they now have metering in every home, and as of this past year, they've been handing out sort of monthly, this is what's happening, this is how you've used energy, this is how your neighbors on average have used energy. So starting to try to create that narrative of the average points that I think we take for granted that BC Hydro gives. You can log in and see what happened 6 p.m. at your house yesterday. So starting to try to create that that knowledge there, but right now at Hot Springs Cove, it's only on the community buildings, prioritized as the large energy users in community for that energy management. That's specifically looking at what we can do to peak load or peak shave and not have the diesel generators go on by maybe not starting on the buildings at 6 a.m. for the day. If school doesn't start till 8, maybe that one goes on at 7, for example.
but is our individual residents paying the energy costs, or is the whole community at once, right?
Yeah, it's still the whole community at once. Yeah. It's really difficult to implement a utility system based on dollar per kilowatt hour when that doesn't already exist.
Yeah.
And maybe when it does exist, people still are not fans, as BC Hydro maybe can attest to. Yeah. Sorry, what were you saying?
It's not metering for you know, for payment as part of the metering system, that you can still monitor CTs, like you can CT up the homes pretty quick.
Mm-hmm.
And that could all be wireless, and you can collect data pretty fast.
Yeah, we've done a lot of different types of yeah, that's a whole other conversation. We've done a lot of different types of metering on individual homes, and I think one of our sort of lessons has been around the importance of narrative in home and what you're using this for. We've used like ones that require Wi-Fi, and then people just like block it from the Wi-Fi, and yeah, really making sure that you're stepwise in the way that you implement meters in homes and communities has been a learning curve for us at Wikino, but that we would apply at Heshquit as well. Okay, thank you.